Hello and welcome to this NFV Architecture and Principles course. My name is Martin Franzen and I will be your teacher for this training. You can see a little bit about my background and expertise down here, if you will. Just, right off the bat, if you see me looking down a little bit like this once in a while during this course, it's not because I want to be impolite or not look you in the eye, although that's, rather difficult anyway during the circumstances. The reason that I'm doing this is because I have a control board at right on the floor in front of me, so that I can, for instance, do this and take away that title. So I will be sort of jumping back and forth between different views, showing PowerPoint. We will spend a lot of time drawing on these fold-outs, so we will have different cameras and so on. And I will be changing between these views by looking down and pressing buttons, so that I have the whole studio at my fingertips, or perhaps toe tips, if that's a word. It is now. I decide it is a word right now. So what we're going to do is we're going to focus on these fold-outs, these papers. I hope you have them in front of you. I have them right here on my table. Also, you need your pens and your ruler, important stuff. You need your coffee, important. If it's morning or evening or midday or night over where you are. This is a good start of the course. Just put that over there. And, well, if you don't have any questions, let's just jump into the first fold-out. So what I'll be doing is I can show you the table like this. This is my first fold-out, the one called Virtualization. So, let's see here. I'm going to take away my 4 pens. I'll put the ruler up there. As NFV is network functions and virtualization plays an important part of NFV. So I will start off by talking a little bit generally about different ways of doing virtualization. I'll show you a couple of PowerPoint slides as well on this topic. And then during this course, we will look more into the sort of specifics of NFV, if you will. I mean, NFV is not just a generic term that anyone can say, oh, if you virtualize some kind of network functions, that's NFV. Well, you can say that and the police won't come and take you, but NFV is also a very specific set of papers written by ETSI, the European Telecommunications Standards Institute. So it's a standard in a way. I'm not perfectly comfortable with calling it a standard yet, because a large part of this standard is still informational. It doesn't have any rules in it that you can break, but they are working towards having it be real rules, sort of essentially blueprints that you can use to build stuff. So NFV is a set of papers or a specification from ETSI. But first off, let's just generally discuss, the foundation, virtualization. Why is this so good? Whoops, there you are. So up here we have 2 gray boxes with sort of just explanations or dictionary lookups. What virtual means and what virtualization means. And you can also, of course, find any number of definitions, but we've chosen one, and as always, it's a little bit of introduction here in the beginning, so I'm jumping back and forth here. As always, I am going to write and draw suggestions in this fold-out. You don't have to draw or write the exact same things. If you feel that, oh, so you use that acronym, well, we actually use another one over here where I work, well, put that in, or put both in, or, put something else in if you feel that I'm lying about something. I hope you don't, but if you really do, this is a suggestion for you that we're offering to you. Also, use the play and pause of this, this method of delivery. Having a recorded training, of course, there's a backside. You can't ask me questions. You can contact us to ask us questions, sure, but you can't do it right now. We have live virtual classroom for that. But the upside of that is that you can play and pause me, which you wouldn't be able to in a classroom, be it virtual or not. So do use that. When I write things here, I won't wait 3-4 minutes and say, oh, have you finished yet drawing or writing? Excuse me, because you can pause me, which is good. And also it makes it possible for you to both write and draw and reflect, which is sometimes a little bit tricky in a classroom situation. People draw and write and copy the fold-out at a different pace. So if you're a slow writer, maybe you're constantly feeling, oh, I just copied what he just wrote and now he's talking about the next thing. Of course, we try not to do it like that, but that can happen, to be honest. In this delivery format, there is absolutely no risk of that, because you can pause, you can write, pause, and then actually reflect on what it was you wrote, or even rewind to see how does this match with this thing he said 5 minutes ago. Difficult things to do in a live classroom setting, I'm telling you. Okay, so that was an aside. Let's go back to this. I will take myself away so as not to block the view. And up here, virtual from dictionary, I'm going to put having the attributes of something without sharing its physical form. So I'm putting having the attributes of something without sharing its physical form, which is almost philosophical in a way. Now, what does that mean? Having the attributes without sharing its physical form. Well, in some cases it's sort of difficult to make it concrete, but some things are very concrete. If you have a virtual network connection, a VPN, a virtual private network to somewhere, well, it feels like you have a cable from one place to another place. It even looks like a cable because it comes out of your wall and you can stick it in a computer or a router or a switch. And in another place, in another part of the world, there's another cable going out that you can stick in another router or switch or server. And they behave as if it's just one continuous cable just, traveling across the world, which of course is not the case. But it has exactly those attributes. It behaves, all experiments behave as if it's one long cable. But it's physically not. It's actually lots of other operators and other cables and fibers and different protocols and so on along its path. So that's sort of one example. Going over to the right side here, virtualization from Wikipedia, the act of creating a virtual version of something, including, and here we're looking to sort of things that are particularly interesting for us in this world that we're working with. Computer hardware platforms, that's the first bullet. Computer hardware platform, so making virtual computer hardware like a virtual CPU, virtual processor, for instance. Virtual storage devices. Storage devices. Think Dropbox. Final bullet is network resources. So I'm putting network resources in there. So network resources, that's essentially, an example of what I just said, a VPN, a cable that behaves like a long cable but is actually some other technology along the way. So that's sort of the baseline here. If we zoom out a little bit, like this, we have essentially 3 sections. Section 1, Section 2, Section 3, with 3 titles. 1, 2, 3. Not filled in yet, but they will be. So these are the 3 areas that we will cover in this foldout. And the first one is without virtualization. So I will put here without virtualization. All in black pen so far. We have our other lovely colors, but still black is the way to go, because I'm going to use those other colors for other things in a moment. So without virtualization, up here we have 2 boxes with little boxes inside. So those 2 boxes are servers. And now I'm going to use blue pen. So we have server 1, like this, all the way over to server N. Server N. And these are like physical computers. They each have a processor, network cards, hard drive. Essentials that sort of create a computer. In these physical servers, we can run operating systems. So here's an operating system, and here is an application. Over here is an operating system and one or many applications. It's difficult to talk and write at the same time. OS, so let's do this. This is OS X, this is OS Y, just different operating systems. And up here is application 1 and application N. Oh, I put applications there, so maybe N and then N plus 1. I had intended to just write application there, but if you feel that this is grammatically annoying, you can put just applications N and O, perhaps, just following alphabetically. All right, I'll just leave it like that, and you can make up your own mind. So here is these 2 physical servers, and they connect down to my big network, which is down here. So we're going to connect all of these different things down to the big IP network down there. In fact, let's do this. Let's put IP network in here, just so as not to confuse ourselves. IP network, like this. And then we can use the green pen to connect these 2 physical servers along these sort of grayed out lines down to the IP network. And they are grayed out so that you can sort of trace along them. And if you want to use the ruler, you can, but you don't need to, because you can just follow it by freehand if you want to. I'm going to do this to make nice beautiful clear green edges like this over there. There we are. So we do have, oh, I didn't fill in the last green line, I can see now. It's no fun if we don't actually reach the end down there. Excellent. So we have a couple of bullets down here pertaining to this left side of the fold out, and then we have bullets in the middle pertaining to the middle part, but right now we're on the left side. So I'm going to take my black pen and write a couple of things sort of describing how this looks without virtualization. So the OS runs on dedicated hardware. So let's put that down here. OS runs on dedicated hardware. It's on a particular place. Can't, easily move it around. It's running on one set of. It may not be built specifically for the application or the OS, but it is in one specific location. However, it can be even built for the application. That's not uncommon in specialized applications in the telco world, for instance. So hardware may be application specific. May be application specific, which is of course a source of inflexibility. Scaling is slow. It's difficult to change this. It's difficult to change it quickly. So scaling is slow. Scaling meaning making it grow or shrink. And redundancy is expensive. You often need to have redundancy for specific applications and operating systems. You need to have a redundant application 1 and a redundant application n, standing next to each other. So redundancy is expensive. Redundancy is expensive, like this. All right. This is all I'm going to write right now about the left side without virtualization, because let's face it, we want to have fun. We want to go over to actual virtualization. So what I will do is I will just write the title here, and the title up here is Virtualization with Hypervisor. So virtualization with Hypervisor, like this. And then I will just jump in and show you a few PowerPoint slides, just as sort of a hypervisor or virtualization intro, and then we will continue on filling in this fold out. So I have here coffee, just remembered. Still good. Virtualization, here we go. Virtualization, comparing the non-virtualized side to the actual virtualized side, it sort of compares a little bit to the foldout that we just drew. Here's hardware, there's an operating system. Up here we have a couple of applications. And it's just, as per usual, the way it's been for decades. There is a big, very conspicuous looking blank space here in the traditional stack, a space that will be filled in once we move over to the virtualized side. The virtualized side has hardware as well. It can be the exactly identical set of hardware, but we have this fantastic hypervisor. The hypervisor is essentially, it's like an operating system that runs other operating systems. See, here we have 3 operating systems. On the left we have 1. Here we have 3 operating systems. They don't need to be of the same flavor of any kind. We can have Linux and Windows running next to each other up here. And of course they can run applications within themselves, or you can run applications within those operating systems. In a way, the hypervisor's job... hang on, backtrack, rewind. I rewind myself sometimes. I will say this another way. These operating systems up here don't know that they're running on a hypervisor. These operating systems believe, or rather you can say they don't know whether they're on the left or right side of this picture. Or you can say they believe that they are on the left side of the picture. They have direct connection to hardware. They actually don't. There is sort of an agent betweener, a translator, a man in between. But they don't know that, because the man in between, Mr. Hypervisor or Mrs. Hypervisor, acts exactly like real hardware. So this operating system believes it has direct access to CPU and storage and network cards and other things. Another thing that I'd like to add in this picture is the fact, just commenting on the name Hypervisor. It sounds a little bit like supervisor, which it is not. It is not. This is not powerful software. Well, it's powerful in the sense that it can do powerful stuff, but it doesn't decide things. It doesn't decide to run this particular operating system with this particular set of hardware. It can do that, but it has to be told to do that from somewhere else. Typically, from a network cable just going in to this big server. This all is one server, one piece of hardware with one instance of a hypervisor running a number of operating systems up there. So this big server has a network cable going into it, and through there you can send a command saying, I want to start 2 Windows machines and a Linux machine. And then we end up with this picture. Final thing I want to add here, I think, maybe I'll think of something else, but final thing that I think of right now that I want to add is the term virtual machine. Because we will be using virtual machine a lot, and it's important to understand what we mean. In this picture on the right we have 3 virtual machines. 1, 2, 3. There are no virtual machines on the left, just to make that clear, because there's no virtualization going on. Here we have 3 virtual machines. A virtual machine is essentially an operating system believing it has its own physical hardware. Remember the fold out? Oh, I'll do this. Up here, having the attributes of something without sharing its physical form. Well, this operating system believes it has access to CPU and RAM and disk and network and everything else. It doesn't have real direct connection. We see that because we have this picture, but it doesn't know that. All the experiments that you can do from up here show that you're on the left side of this picture. So this is the attributes. This is the way it would look, but it doesn't share physical form, because we see the reality is different in the left side of the picture as compared to the right side of the picture. So virtual machine essentially an operating system running on a hypervisor here. So what can we do with this? Well, we can do this. We can distribute the resource usage more evenly. We have 3 customers here. They use their resources very differently. Customer A uses almost all these resources, all the way to the other extreme. Customer C uses almost no resources. They have the same amount sort of assigned to them. It would be better to have some kind of a controller that controls these 3 servers. And maybe it's the exact same amount of total computing power, however you would measure that. But then you sort of spread out these customers over these 3 physical nodes. So customer A, who apparently needed a lot of power, a lot of computing power, uses resources on all 3. And quite a lot as well, if you sort of look at the height of these bars. Customer B, slightly less, uses 2 nodes and lower bars. Customer C, even less, so even lower bars, but still spread out a little bit on the middle node and the rightmost node here. This means we can have an average load on these physical servers that is much more even and much more not in the extreme end of the scale. This picture could be what it looks like on a sunny day where everything is working fine, so it's exactly this. If something breaks down, let's say this server breaks down, hopefully we have some kind of warning. You can have discussion about what happens if you don't have a warning, and then you need redundancy and backup of data and so on. For the purpose of this discussion, let's say we have some warning. It's sort of a controlled breakdown. We know that the disk is starting to fail. We need to change it. So what you do is you move all the things that used to run over here on the rightmost node to spread it out over the ones that are left, like this. And then we send out this very competent looking fellow here to repair the broken server. During this time, the maintenance time, of course the load is higher, but it's predictably higher. This is deterministic because we know exactly how much power we used up there. So we can easily calculate, do we have room to move that into these 2? Yes or no? Well, apparently yes this time. And then he exchanges the broken server for a brand new one, and then we migrate the functions back, and then we're back to the same average load as we had at the beginning of that story, which is good. I use the word migrate there, and you can sort of stick it at the back of your mind for the time being, because we're going to come back to it. Migration is something that's very interesting when it comes to virtualization and virtual machines. Moving stuff from one physical location to another, we call that migration. Finishing off this small PowerPoint breakout session, we can look at who uses these servers. We have 3 servers here. We have hypervisors installed in all of them so that we can run virtual machines in all these 3 locations. Now, in this example, there is one user, the green user. It says different tenants here, so they sort of rent space in these computing nodes. You can see these colors as different companies, for instance, different organizations, different customers. And the green one has the sole usage of the first one, and red is in the middle and purple is on the right, which again leads us back to a little bit of inflexibility. Now, what if the green one wants to extend? Can he move into red? Well, no, it seems at least like red doesn't want that. He wants his own little sort of playing yard here, and purple wants his space with fences around. This you can buy this, and you can pay for this, have dedicated hardware for your virtual machines, but it does limit the flexibility, and it's not sort of the final aim. The final aim to have multi-tenancy like this, so that you accept that customers or different customers from different organizations are allowed to share the same hardware. They won't be able to affect each other because we have security principles and policies and so on in place. So if you don't mess things up, this should technically work the same, or maybe you should say perceptually work the same. Again, if you would make an experiment from the red world, or from the green world, or from the purple world, sort of from the outside, logging into a machine and just doing whatever experiment you can, you shouldn't be able to tell whether you're on this slide or on this slide. It should look exactly the same. It's just the company actually running these servers, renting them out to these customers, that know whether it looks like this or the previous slide. All right, so that was a bit on virtualization. Now I suggest we go back to the foldout and fill in this middle thing here, because now we have covered a bit of ground, so it will be easy to fill stuff in. So let's do this here. First off, this is also a server. I will call this server A. Just to sort of basically just agree that this big box here is one server. This is not a collection of servers or a data center or something. This is one server. And here we have CPU, network card, hard drive. We have the hypervisor that we talked about, so I'm going to put that in here. Hypervisor, like this. That's this big black box here, which means we can run virtual machines. So up here is virtual machine 1. So I'll put that in green. Virtual machine 1. And there's a reason why I put this in green, because I'm going to use green to map out how much of the real physical CPU network resources and storage that the green virtual machine is allowed to use. All right, so the virtual machine up here believes it has a CPU. It's right here in the left. I mean, just like this big machine has CPU, NIC, and hard drive, these virtual machines have CPU, NIC, and hard drive. We will call them virtual. So I will put V CPU here. Virtual for V for virtual, of course. Just to repeat, the hypervisor knows this is a virtual CPU. The virtual machine does not. The virtual machine believes it's over here on this side. Just here's a server, I have some CPU. But as we are almighty and see this sort of from the side, from the outside, we know that this is actually a virtual CPU. So it has a virtual CPU, it has a virtual network card, network interface card, and virtual hard drive, like this. And then the hypervisor allows this virtual machine to make use of some of the real resources. Not all, mind you, but some. You know, depending on policies. Someone has started this virtual machine, configuring this virtual machine to be allowed to use. Now I'm going to draw a little bit of green here. I'm going to give it this amount of CPU. So it's not the full CPU, but fairly chunky part of it. The network card, so you could see of it as bandwidth. For instance, if you feel, how do you split up a network card? Do I get half a cable, or just 4 of the 8 wires, or something like that? You can see of it as, for instance, as just bandwidth. I have 1 gigabit of bandwidth. This virtual machine gets 100 megabits of those. And hard drive, I'm going to give it some storage as well. So now that we have started this machine, we have sort of created a virtual machine that has what it believes to be physical CPU, network card, and hard drive. We can boot up an operating system. I'll use black here, OS X for instance, and start applications. Application 1. So it could look just like the left side here, only it's all running in the same server, server A. And as you might have guessed, we have given green some usage down here in these resources. Now we need to give someone else access to the rest of those resources. And someone else is virtual machine N. Virtual machine N. That's an ugly N. There you are. Virtual machine N. It has its red virtual CPU, its red virtual network card, and its red virtual hard drive, like so. And this is actually a little bit smaller when it comes to processing power, I have decided, arbitrarily. So I'm going to give it this amount of CPU. A little bit more network bandwidth, actually, for some reason. And let's say about the same amount of hard drive. And now we have booted up this, or rather we have sort of created the physical prerequisites to boot up a machine. So now we boot it up with operating system Y and application N. This time just application. There you go. All right, so this should give you a fairly good understanding of how we sort of split up the real physical resources down here among the virtual machines. Now, we do have some bullets down here. So I will actually first let's just connect this. See the line here goes down to our IP network. We have the real physical side coming down from the left over here, so we need to connect this now. So let's take out the green pen. And do this and that. And perhaps you will actually hit the line a little bit better than I just did. And then we can start writing some things about the virtual machine. So first I will just put virtual machine, and since this is an NFV course, NFV comes from Etsy, we will use the way Etsy describes a virtual machine, which doesn't differ a lot from how others do it, but we just had to make a choice. Etsy terminology. Don't believe that this means that virtual machine is an Etsy word. I realize that you might interpret it like that. If you feel inclined to interpret it like that, add something else to sort of to take away that belief. This virtual machine is a very global concept, and it's a very general term that is used and has been used, by all different kinds of organizations and standardization works and institutes of education and so on. So it's just, since NFV is it's an Etsy thing, we sort of use the phrasing of the virtual machine description that comes from Etsy. So it's essentially a software version of a computer. Software version of computer. Because up here, the reason why we say that is that up here, the hypervisor and vCPU, vNIC, and vHard drive, that's all software. The virtual machine up here, the OS and these applications, they believe it's a real physical computer that you can sort of lift from the floor and drop on your toes. But it's not. It's the software equivalent of that. Again, it behaves like that. It has those attributes. It has the attributes of a real CPU, but it doesn't share its physical form. It is actually just software here. This is the physical CPU. This is software, making use of the physical CPU. So it uses resources provided by a hypervisor. It uses resources provided by hypervisor. And the way to describe a virtual machine is, well, how would you describe the physical machine? Let's do this. Just move it over like that. This physical machine. How would you describe this server N? Well, I can describe, sort of the OS and the applications in it. Okay, so how do I do that? Well, all of that sits on the hard drive, right? The operating system is on the hard drive. Those applications is on the hard drive. So if you just make a copy of the hard drive, you can take that copy. Maybe that copy exists as a file, so you can put it on a DVD or a big USB stick or something, and then you just go over to another physical machine and just insert this operating system with its application, and then you can boot it up. That's essentially, you can do that. You can boot from a hard drive. As well as you can boot from a hard drive, you can boot from a CD or DVD or a USB stick for that matter. So you can just copy all of that. That is usually called an image file. The image file is sort of a snapshot of all the ones and zeros on this hard drive of this computer up here. That's not enough though, because if I do that and insert it sort of on another physical machine, maybe that physical machine has other physical attributes. Maybe this application N needs a lot of CPU and a really fast network card. And then I move all of this using an image file. I copy it over to this server that has maybe a lot less CPU and less powerful network card. Then it won't work. So in order to describe this whole server, I need to describe this up here, the applications and the OS. I use that for an image file. And then I need to describe the physical machine in which this is running. So I'll say, I have this amount of CPU. I have this kind of network card. I have this amount of hard drive. I have this amount of RAM. And I have this amount of different kinds of disk and so on. That is usually called metadata, sort of on the side data, or data that is sort of relatable to the main core. So the main part is the image file, and then we have metadata describing the actual physical machine. Up here it's the exact same thing. An image file would contain the OS and the applications. The metadata will describe virtual CPU, virtual NIC, virtual hard drive, and maybe other sort of physical attributes or physical resources that could be mapped down here from the real server up to the virtual machine. So let's put down here on the final bullet on virtual machine, described with an image file plus metadata. Described with an image file plus Metadata. Metadata. You could put, let's put hardware description if you want to. I will put it below like this. Hardware description. Like this. And then a couple of words on the hypervisor. This thing, fooling the virtual machine to believe it has real physical resources. So, hypervisor performs virtualization. Performs virtualization. Essentially the act of tricking the higher layers up here to believe it has access to physical resources. It provides access and control of the hardware to each VM. I mean, that's these dashed lines here, right? It provides access to the CPU and control. So it can control things. It can send things out through the network card. It can store things on the hard drive. So it controls its part of these resources. I mean, the green machine only controls the green part. It's not allowed to do anything in the red part naturally. But for the green part, it can exercise a bit of control there. So the hypervisor provides access and control of the hardware. Access and control of hardware to each virtual machine, to each VM, like this. All right, almost done. We have 2 bullets left, but it's easy because we have pictures to sort of describe what we're drawing down here. What we're writing down here. So the next one will be partitions physical resources and allocates them to VMs. So that's exactly what we see here, the partitioning of the physical resources. Lots of green, a little bit of red. Rest is as of yet unused. So partitions physical resources and allocates them to VMs. And allocates them to VMs. And finally, as you know, relating hypervisor to the concept of operating system, the hypervisor is essentially an operating system. VMware has a hypervisor called ESXi, for instance. That is an operating system. Linux has a hypervisor called KVM, which is it's not an operating system. It's actually a kernel part of the operating system that sort of installs itself in the lower part of the stack in the operating system. So what I'm going to write here, maybe a little bit confusingly, I will write is or runs in an operating system. All right, so it can be an operating system or it can be part of an operating system. So is or runs in an operating system. Like this. Is or runs in an operating system. So now we've actually covered 2/3 here. We have the rightmost side left, the rightmost side left, or the leftmost side right. this is the rightmost side, and we're going to put containers in here. Virtualization with containers. So let's put that title in. Virtualization with containers. Which some people even would argue is not real virtualization. It's just a language thing. Some people would argue, no, hypervisor, that's how you virtualize things. Container is something else. But more and more, the world is sort of saying, well, containers is one way to virtualize things. So I will show you. This was where we left off. So I do have a couple of slides here on containers as well. So I was planning to show them to you before we just draw and write the final things on the fold out. So what is a container? Well, a container is something that comes from the Linux world. It doesn't need to be only in the Linux world, so it's spreading outside of it, but it sort of comes from the Linux world. So what it does is it says it creates an environment as close as possible to a standard Linux without a separate kernel. A kernel, that's the innermost part of an operating system. So another way of saying this is these red dashed lines up here. I can zoom in a little bit like this. These boxes, the red dashed boxes, they are like virtual machines. Okay, they behave very much like virtual machines, but they don't have separate operating systems the way we did with hypervisors. There's only one operating system below here on which we run these containers. So another way of saying the same thing is a container is essentially running applications saying, when you run them, that you are allowed to only use resources inside this box. You will never be allowed to see anything in that box, whatever's running in there, or in that box, whatever's running in there. And we do this with essentially policies. Policies, and Linux is very good at keeping these policies, these borders, these lines super tight so nothing slips through. So that's this. Use kernel features for separation. That's those policies that I just talked about. Near bare metal performance, bare metal is the physical hardware, the real CPU and NIC and hard drive essentially. So when we have a hypervisor, we sort of do install an extra layer of abstraction that can add a little bit more processing time and so on. Here we don't even have that. The applications in the container talk directly to the real operating system, the only operating system existing in this node, which means we get quicker response, and more primarily very much quicker startup time. So it says here fast provisioning time. Provisioning means essentially booting up, starting times. So we have a scale down here with time and then 3 different examples. Physical means no virtualization at all. Just you buy a physical server and install things on it. You get your CD or DVD and put it in and install things, and that takes days is an understatement here in order to install complete complex things. Physical, this can take weeks or months or sometimes years if you include procuring the things, getting the physical servers and getting them to the right data center and so on. A virtual machine can be booted up, providing you have the blank hardware ready. A virtual machine can boot up in a matter of between seconds and minutes. It's essentially the same time it takes to start any machine. Just boot up. That's normal boot up. Just go up to a machine and click on, and then wait until you have a prompt or a window screen or whatever you want. That can take maybe 30 seconds, maybe a minute. This LXC is short for Linux containers, and this is like sub-second. You can start one up in less than a second, and that's because you don't really start anything. You don't boot up a machine. You just start an application the way you would have anyway, and just say, you, Mr. Application, are only allowed to exist within this little world. So it's very, very quick to start a Linux container. If we compare Linux container to virtualization with Hypervisor, here we have hardware, Hypervisor, operating system, and applications. There is something called hardware assist that I won't go deep into now. I'm just mentioning it since it's part of the slide here. Hardware assist is a way to make the hardware down here extra good at running hypervisors. So that's essentially what it means. It doesn't mean that the OS up here is informed in any way or know that it's virtual. The OS up here still thinks it's on its own dedicated server. Still, that's not the point of this story here, because we're talking about the containers. So here we have hardware, hypervisor, OS, and application. With Linux containers, we have hardware, we have an operating system, typically Linux. Then we have any application. You know, before the container entered the stage, it just looked like this. But then came this, containers. So in here, in these containers, we can run applications. These applications in here can see this application that doesn't run in a container, but it can't see anything in that container. What is a little bit cool as well is that we can include things in these containers that are required by the applications. An application requires binaries and libraries, that's bins and libs here. That's essentially code, precompiled or non-compiled code that sits down here in the operating system and that the application can make use of. So when you install an application, it's very important that the binaries and libraries that it needs exist here already. And if they don't, you have to install them. You need to find those. Those usually go under the term dependencies when you install an application. So what you can do in a container is you can install an application and then just, pre-pack, just add all the binaries and libraries that this particular application needs. That makes this a very self-sufficient unit here. You can take this container and move it to any Linux operating system that supports containers. You don't need to care about the binaries and libraries that happen to exist in that particular machine, because the container carries them with it, which makes it very flexible. So these containers run in the host system's kernel. This is the host system, the mother Linux. Separated with policies, you can use applications in the host system, but you can't see the applications in another container. You can install additional libraries and applications. It is portable between all the operating system variants supporting Linux containers. And there's no overhead with a hypervisor. So here, this hypervisor adds a little bit of overhead, as little as possible, but more than zero. Here it's essentially zero. So comparing these two don't compete with each other. This is, hypervisor is good for some things, container is good for other things. Hypervisor is slightly more secure in a way, because if you have a virus that crashes its operating system, it will only crash its operating system and not the neighbor one. If this application crashes its operating system, well, there's only one, so this whole right side of the picture will go down in flames, as they say. However, there is so that's sort of better on this side. This one is much more flexible in the way that you can boot it up much more quickly. If you do a Google search today, a little container will boot up just to list your results, and then it will die. It's almost like a subroutine in programming. And big companies have lots of these containers just for small functions. Just add these numbers, create this list. Okay, start a container, create the result, and then the container dies. You wouldn't be able to do that with a virtual machine running on a hypervisor, because it takes a minute to boot the machine up as opposed to less than a second. Right, boots in less than a second. Boots is sort of a, not maybe the exact right term, just starts maybe. Finally, Docker is a way to use containers that I thought I could inform you of, because you may come across Docker. It's not its own thing. It's just one kind of container, one brand, if you will, of Linux container. So this is the picture that we just had. It's had sort of a low-level API, application programming interface, with commands for how to start and stop these containers. And if you're not a super hacker, maybe you feel that this is difficult to manage. So Docker installs itself as software here that essentially makes it just more easy to manage those containers. But the containers are the same. It's the same kind of containers. So Docker is better at that. All right, do I want to say anything more about containers? No, that's pretty much it that I want to say about containers. Now let's go over to the foldout and fill in this final little corner of the foldout, and then we'll be finished with this first lesson of the course. So we have virtualization with containers, and essentially I won't put anything very much new here that wasn't in the presentation. We have one operating system down here having access to its physical resources. Here we can run containers. So this is container 1 and this is container N. And in these containers we can run applications. So I will just put application like this. If we want to just remind ourselves a little bit about what this was, this is Linux containers LXC. It runs on host OS. Meaning the operating system that really is installed on the real physical hardware. It's policy separated. Policy separated, and it boots fast. I will put boot in quotation marks like this. Boot, it's supposed to be 2 O's here, right? Boots fast. Hang on. I want to do this. Boots, so I will turn this into a nice exclamation mark like this. Boots fast. And also we need to, of course, connect our computer running containers to our whole IP network at the bottom of the page. Like this. So we have our 3 different sort of ways to do virtualization here. We have without virtualization, or 3 ways to run applications, I suppose. 3 ways to run operating systems and applications. Without virtualization, the traditional legacy way, with Hypervisor and with containers. The final thing that I want to add here is just a little bit down here, because we're not going to mention cloud very much at all during this course. We have other courses that talk much more about cloud, but we wanted to sort of get it in some way here. So down here we have sort of a dashed line going across like this through this IP network. And this is in order to show you that there is a user out here. So this below the dashed line is the user side of things, meaning he doesn't see all the details up here. From here, he absolutely can't tell whether his application is running on the left side, in the middle, or on the right side. He just sort of logs into a web page maybe and clicks around. Up here is the cloud side. So I'll put that in quotation marks as well. This is the cloud side, and you can zoom in a little bit still. Our favorite description of what cloud is this: network access to shared resources. Resources to you there. And the cloud interior is not visible for the user. So I'll put that down as well. Cloud interior not visible to user. So from outside here, you have network access, that's this IP network here, to shared resources. And you can share resources with other users in all of these three different parts. It's just much more difficult to provide shared resources without virtualization. You can, but it's much less flexible, so it's difficult. Here it's much easier. I give one user a virtual machine and another user another virtual machine. With containers, I give one user access to this container and another user access to that container. All right. So that was the end of the first fold out of this course, the virtualization fold out. I hope you enjoyed that, and I will see you in the next lesson. Bye now.